Next presenter is Unmesh Bordoloi. Unmesh is a senior researcher at General Motors R&D, where he's working on computational platforms for autonomous driving. Prior to this, he was a faculty member at Linköping University in Sweden, where he obtained a tenured position. He also spent 1 year as a postdoc at Verimag, France. He graduated from National University of Singapore with a PhD and from National Institute of Roukelen with a Bachelor of Technology degree. And today, Unmesh is going to talk, his presentation is on collaboratively benchmarking and optimizing deep learning implementations.
Good afternoon, everyone. Thanks for the introduction. I would like to, at the outset, acknowledge my co-authors. This is a joint work between General Motors R&D and a startup company in England, DVDT. And of course, we also acknowledge the contributions of the larger team. I would like to start the talk with a small video. I'm just curious how many in this audience have heard about the company Cruise Automation. That's actually quite a few. Cruise Automation is a startup in San Francisco that General Motors acquired last year. And my second question is, how many of you have heard about the Chevrolet Bolt vehicle from General Motors? Slightly better, but still, I can let me explain that it got very good reviews, and Chevy Bolt is got very good reviews for being affordable and long range, the first affordable and yet long range electric vehicle. So this video shows the Cruise Automation team efforts of putting their software for self-driving on a Chevy Bolt and running through the streets not far from here in San Francisco, right? So you can see a small video embedded within the larger video on the left-hand side showing how the driver does not need to interfere while the car is navigating constructions, pedestrians, bikes, traffic signals, and so on. While we look at this video, I would like to highlight some of the headlines over the last year where GM invested in Lyft. I already told about this acquisition of the company called Cruise. We have also seen in the news GM has said that the vision is to first bring self-driving cars in the domain of ride-sharing vehicles, right? Then there is a lot of news about competition as well. We have heard a lot about the Google vehicles. There is news about Baidu, Uber, and BMW, and so on, right? I cannot cover all that news here, but my point is that if we look at all the stuff, it seems like, hey, we have solved this problem, right? So what's next? What am I doing in General Motors offices in Michigan, right? In order to look at what's up in future, I usually start by looking at this picture, which is quite reflective of the traffic situation in my hometown. So I think we have lots of opportunities for optimization when we try to have autonomous vehicles that are available everywhere and are affordable for everyone, right? And this topic of affordability relates to what I am going to cover today, is that among other factors that contribute to affordability, computing costs are a major contributor, right? If we look at the major components of an autonomous car in the software pipeline, it starts with the sensors that process the raw data that comes in, some kind of fusion. We need to understand the scene. We need to do some planning of the behavior of the trajectory, and then we have some control algorithms, right? As is evident from many of the talks in this summit as well, many of these tasks they have deep learning as their key enabler. Please don't take this slide at as literally. It just shows a high-level conception view of how it to highlight the fact that deep learning is really important, and it really has very large computational needs, which brings us back to the challenge of making it affordable, right, in terms of computing costs. So understandably, when we started with deep learning, the community developed a lot of the frameworks and algorithms on high-performance machines and in the cloud, right? But when we want to have this capacity inside the car, that's a challenge. We want to get this cloud and servers out of the picture. And it's not just about performance, but there are many other metrics that we need to worry about. And they are about what's the form factor, where can we put it inside the car, what are the safety dimensions, what about functional safety, what about the thermal issues, power dissipation, and all of these topics on their own merit a significant discussion, right? For the purposes of this talk, however, mostly I'll be solely concerned with performance or latency. So that brings us to the kind of what I would say the main message that I would like to deliver here is we have a problem where we need to select the hardware, right? And there are many competing solutions out there from different vendors with different technologies, right? Given my background in computer architecture, I thought, hey, this should not be so difficult. I did quite well in my studies with computer architecture. I can figure this out. So then we started to dig the surface a little bit, and what I found was a real mess, right? We have so many choices. Our experts are working on cutting-edge technologies. They are developing new algorithms. They are taking different kinds of problems: classification, object detection, segmentation. There are different algorithms and models that are being developed, what I call at the top layer of this hierarchy, right? So even if you talk about one of these problems, there are different representative algorithms. There's LXNet, ResNet, GoogleNet doing classification. There's SSD, YOLO for object detection. And these are kind of single shot approach. And then you have RCNN and so on, right? So, and for each of them, you have a bunch of parameters that you can play with and optimize, right? And then on kind of beneath that, in my opinion, there are the frameworks that experts prefer based on their needs. There is Caffe, there is TensorFlow, CNTK, PyTorch, Torch. Each comes with their advantages and disadvantages. And the experts, they have their preferences on them. Then they are powered by the backends, the libraries that we need to plug into them when we are trying to accelerate the algorithms that run on the top, namely different kind of BLAST libraries, right? There is CUDA cuDNN from NVIDIA. There are some open source libraries, libDNN, CLBLAST, CLBLAST, and so on. So at the end of this, all my arrogance was gone, and we were frustrated. Now, what can we do to how can we bring a systematic benchmarking effort that can kind of look at this cross-layer parameters so that we can make an apple-to-apple comparison? And the way we are approaching this is with a tool and a framework called collective knowledge, and that's where our partners called DVDT come in. Right? So we hope, and this is our goal, where we will try to reach there, is to have all these choices, and I'm not able to list all of them here, kind of being able, being as parts of a Lego toolkit that we can plug and play into this framework called collective knowledge, and then it will give us the results that we are looking for, comparative benchmarking and optimization, right? So what is collective knowledge? What is CK? I think at this point it is good to have a quick introduction to that. It is a technology. It allows you to create and to share, to reuse artifacts that you create. Yeah? You can create experimental workflows. You can share your data sets, your models that you have, and so on. It's cross-platform. It's not limited to either Windows or Linux. It's customizable. You can plug and play the modules that you build. It's open source. You are welcome to download and start playing with it, and it's a lightweight Python-based package. It's not just a tool, but I see this as kind of a philosophy, a methodology that allows systematic and reproducible experimentation. It allows us to and encourages sharing of artifacts. We actually invite the community to participate in this and collaboratively find unexpected behavior that may be hidden if without a shared or crowdsourced approach. And that brings me to the fact that the tool allows you to crowdsource this benchmarking results, right? What we have achieved so far is to build kind of what we call CK Caffe as a wrapper around Caffe. It shares the same traits as the tool collective knowledge. It's kind of an extension of that. So it shares the features of being cross-platform, supported on Linux, Windows, and Android. Customizable, so you can quickly extend this with new models and forks of Caffe data sets. It's open source, and again, based on Python package. So if you want to get started on Caffe, I welcome you to go to the GitHub page, CK Caffe. You can type CK Caffe or C knowledge on your favorite search engine, and hopefully that will take it to this repository. And just to give you a quick highlight, you need to just follow a set of instructions over there that's listed in order to get started there, and just need to install it, write few instructions in your command line. With that, I will talk about few results that we have achieved so far with this tool. And while I cannot talk about all the platforms, the results here are on the NVIDIA GTX 1080, the Tegra TX1 from NVIDIA, a couple of others for which I'm unable to show the results. The networks for which I'm sharing the results are LXNet, GoogleNet, SqueezeNet. There are two versions of it. And I will not talk about the best neural net in the world that is in General Motors. And then there are a bunch of different libraries that we have plugged into this framework. CUDA, half precision and full precision, cuBLAS, those are from NVIDIA. libDNN, it's an open source DNN library. CLBLAS is our open source libraries, OpenCL libraries, and OpenBLAS is an OpenCL library for the CPUs. So this is the first deck on slides on the results. This result is, these are on the NVIDIA GTX 1080. The x-axis shows different models that I talked about, starting LXNet, GoogleNet, SqueezeNet, the two versions. On the y-axis, we have execution time in milliseconds per image. For each model, what we show here are the varying execution time taken for the same model and for the same batch size. And you can see how widely it varies. It's not a surprise that the NVIDIA CUDA is the best optimized. It's an NVIDIA platform after all. But there are reasons why we might be interested in a variety of libraries, non-proprietary libraries. And so it's interesting to see some of them coming quite close to that. In particular, if we look at the results from libdn and CUDA across all the models, this is the third from the left and the fifth from the left. So they are quite close to each other, right? Of course, this libdn still relies on the CUDA implementations library from NVIDIA, right? But with all the results that I'm sharing here, I would like to come back to the problem that I highlighted. It's that of the benchmarking. There are so many different parameters, and here we are just looking at one of the layers, which is the choice of the libraries, right? We have heard a lot in the previous talk, again, about the choice of the libraries. There are libraries that are being redesigned for optimizations. SqueezeNet is an excellent paper. It managed to squeeze the parameters by a significant margin when compared to LXNet, and is still delivering same accuracy levels. There are further recent papers out there. We have not managed to get the results for them yet. But what this shows is a comparison in terms of performance for SqueezeNet, the two versions we had, versus the LXNet. So the y-axis is again the execution time per image, and the x-axis is three different libraries. It's the CUDA, the library, cuBLAST library is the first one from NVIDIA. The second one is the NVIDIA cuDNN library. The third one is the libdnn with CUDA, right? And for each of them, we have three plots. The first one, the red one, is the LXNet results, and the rest of the two are SqueezeNet results. I think the most interesting is the plot in the middle for NVIDIA cuDNN library. And say, yes, SqueezeNet for GTX 1080, we did not observe any performance improvements. Yes, for libdnn and CUDA, using that as a library, we did see some improvements, but that's not where we get the best performance. So again, it's one more kind of point in the selection across the layer that we need to think about when we are benchmarking in order to get an apple-to-apple comparison. By the way, we got similar conclusions on GTX 1080, although I have not shown the results here. Sorry, I need to clarify here. So these results were on TX1, and we got the trends were similar on GTX 1080. If you are working on GPUs, you're very familiar with the concept of batch size. We have heard in several talks today already about the importance of collecting items together and sending them to the accelerator. It increases the throughput. However, as the batch size increases, you compromise on the latency, and latency is an important factor when we are dealing with a real-time application like a self-driving car, right? So here you can see the impact of batch size. Batch size is varying on the x-axis, and on the y-axis, again, you have execution time per image. It's, to be clear, it's not the latency, it's the execution time per image. And you can see that with increasing batch size, you do increase the throughput, so the execution time per image comes down. These results are for SqueezeNet on NVIDIA, and this is with the TensorRT inference engine from NVIDIA, right, with half precision. I realized that there is one plot, one curve missing here from this plot, which shows the memory, but that's a non-trivial result. That's a very trivial result. It just increases with the number of images that we have. And again, we have similar conclusions on GTX 1080. Yet, talking more about the parameters that we need to be transparent about when we are doing this kind of benchmarking. Here we take the data types to look at the impact of precision. This is GTX 1080. On the y-axis, once again, we have the execution time per image. On the x-axis, we have different models. And the red curve, the red plot shows NVIDIA cuDNN running at full precision. And the yellow column shows the NVIDIA cuDNN at half precision, right? And these results in the beginning were very counterintuitive to us because lowering the precision actually deteriorated the performance results, right? So this, and when we spoke with the NVIDIA experts, we figured out that actually GTX 1080, despite being the Pascal architecture, it has very limited support for half precision. So there is an overhead in working with the half precision. Now, if we look at the same results on if we when we did the same experiments on TX1, which was actually a previous generation product architecture, we got different kind of results where I would like you to first focus on the two plots at the left of each of the models. So let's take GoogleNet as an example. Let's take the two bars at the leftmost, which shows the NVIDIA full precision and NVIDIA half precision with the CUDA library. And you can see that the execution time does show a significant reduction, improvement, right? So again, with this, I wanted to drive home the message of being transparent in these parameters. There are so many different parameters across this, what I call the deep learning implementation hierarchy, which are important to be exposed when we are doing such a benchmarking activity. Let me focus on one more thing on this slide, which is the use of the TensorRT tool from NVIDIA. So those are the plots on the right-hand side for each of the models. So for example, if we take a SqueezeNet 1.1 at the extreme right, we have the yellow bar and the orange bar, which are the two rightmost bars. And you can see the TensorRT full precision is better than NVIDIA CUDA and full precision, right? So even at full precision, TensorRT, without lowering the precision, does give a better performance. And that's because they have, NVIDIA has implements in this tool. They take care to implement, take the model and they try to optimize it for inference. And of course, when you go TensorRT half precision, the results are even better. This is the last slide that shows the overall, that puts all the optimizations together for TX1. On the y-axis, this time, instead of execution time, we have images per second with the best batch size. And on the y-axis, you have the models. And we show the results for different choices that we ran, starting from OpenBlast, which is a CPU implementation at the left for each model, going all the way up to TensorRT half precision. So one way to read this plot will be to look at LXNet and look at what we can get on the CPU with OpenBlast. And it's kind of 8 images per second. And then if you look at the CUDA library, which is the fourth from the left, we have 135 images per second. And then if you use TensorRT and go for half precision, you go up to 336 frames per second. And now if you want to, again, think about this bigger picture and looking across the hierarchy and think that, hey, SqueezeNet maybe delivers the same accuracy, why don't I look at SqueezeNet? You can see that for each of these corresponding points, you are doing better in SqueezeNet, especially when we look, let's look at SqueezeNet 1.1 for that. And at the extreme, we get 532 images per second. Similarly, we can look at the results from GoogleNet, and it brings out the trade-offs using this with the choice of libraries, the choice of underlying hardware, whether it is CPU or GPU, is full precision or half precision, using TensorRT or not, and so on. That brings me to the last part of my talk. Like I said, I would like to take this opportunity to invite the community to participate in a collaborative benchmarking and optimizations. we are already starting on this with together with DVDT and some chip vendors. It provides validations to the numbers that we see in marketing slides, because this tool really allows us to reproduce the results by packaging this experimental workflow so that I can quickly take this workflow from you and run it on the machine once I have it. So the results are very easy to be reproduced, and we are on our march forward, looking forward to engage student and academic communities, participating or sponsoring competitions and engaging university professors and groups with this tool that we have. We have just scratched the surface. I think there is a long way to go. There are many parameters that we have not been able to benchmark, many other models, there are other frameworks, so there is a long way to go here. I think this is my last slide. I cannot not put my academic hat whenever I give a talk. So there are a lot of open problems, in my opinion, for the scientific community to tackle. So for example, when we, at the automotive company, we are very concerned about predictability in performance, right? So how do we bring the real-time community, who have a lot of experts in giving performance guarantees and certificates in real-time performance, and blend their expertise with the new applications that are being developed in deep learning, right? So they are used to working with a lot of formal models. How can we extract such models from the applications and workflows that we are working on right now? And then typically for deep learning, we are using accelerators, GPUs and FPGAs, DSPs, and it's already difficult to talk about worst case execution times, so giving bounds on the execution times on such accelerators for relatively simpler examples, and it's also a challenge to give some bounds already on multi-core CPUs and out-of-order CPUs that have, for example, out-of-order executions and other microarchitectural details. So how can we again take those, the expertise and the research being done there, and learn and merge together with what we are learning in the deep learning community? I think from a researcher at the automotive industry, this is what I see as some of the other open questions we need to talk about. That's my concluding slide. These are links to go to the C knowledge and where you will find more descriptions about the collective knowledge tool. You can download CK Caffe from this GitHub link that we have here, and the video that I showed from the company acquired by General Motors, Cruise Automation, and other videos from them you will find at their Twitter link. In fact, they have recently released one video where they are driving through the streets of San Francisco at nighttime. With that, I conclude my talk. Thank you so much.
So maybe one question. We're kind of at the top of the hour. Gentleman here.
Thank you. Great talk. Enjoyed that. Question about the definition of architecture in this case. It's a fairly complex space, as you kind of articulated. This is just the tip of the iceberg. But do you worry about the fact that by describing numbers on specific architectures, let's say an N-core CPU and a GPU, whereas architectures have got issues in terms of on-chip communication, memory accesses, caches, a lot of factors go into that communication and that numbers that you eventually write out. Is there a concern that these numbers may be a little too conservative or maybe completely out of the picture in terms of new architectures coming out?
I'm not sure I get the question 100%. So let me repeat the question. So the question is, we have shown some results here, and there are new architectures that are coming up. How do these numbers compare with the results that we expect on other kinds of architectures?
Or even to the extent that these numbers are representative of what people are seeing out there?
We are very confident in the results that we have right now with our tool. And like I said, we welcome everybody to download them and rerun and tell them if there are any discrepancies. In terms of the other architectures, newer architectures that are coming up, and how will these compare to them, it's, I think, very difficult to say.
Okay, if we could thank the speaker again. Thank you.
Thank you.